This is lecture number 3. Let me just give you a quick recap of what we have done so far. We have discussed about signals, the basic types of digital signals, which is a unit step and a unit impulse. Then we spent some time in learning about the basic operations which you perform on signals, and they are on sample by sample basis. So whenever we say you are adding, subtracting, multiplying, so you need to keep the indices of the samples in mind, and only you can operate on indices, especially once you are doing addition, subtraction or multiplication. Then we also discussed the delay, ideal delay, where you just take a signal and delay it in time by d samples. Then we learned about this general mathematical representation of a generic signal. Any signal can be represented as a summation of weighted shifted impulses, that you disintegrate a signal into impulses, and once you add them together you get back the signal, and this is the mathematical representation. We say that it is a summation of shifted impulses weighted by x of k. Then this is the representation of signal in terms of impulses. Then we talked about the time domain analysis, and there we said our interest is in linear and time invariant systems. Somebody asked me a question: what if is there an example of a system which obeys one property and does not obey the other? For example, absolute is, if you are taking absolute, it will scale for positive values, right? It will scale for positive value, but once you add, it will not work, right? Because again you can do 1 and minus 1, so you add them, you'll get 0. But for positive value it will scale. So you can always come up with systems which will obey one property of linearity and won't obey the other. Same is the case with maximum. Maximum will work for the positive, will scale for positive alphas, but it won't work if you add them together. Minimum, maximum, absolute, these all are examples of non-linear systems. Okay, so and I'm just saying positive value, but then you can come up with another system where you say, okay, I'll take the maximum value. So if I'll always consider 2 samples. So this is a system. I'll consider 2 samples, and I'll keep the one which has greater magnitude. Okay, this is an example which will scale a greater magnitude. So let's say if it is 2, it is minus 3. So I'll keep minus 3. So this is a non-linear system. It will scale, but once you add them together, it will not work. Right? So you can come up with these type of examples. I emphasize that it needs to obey 2 properties. Okay, so we discuss linearity in detail. This is what is meant by linearity, that it needs to obey additivity and time in the scaling property. And then we consider systems which are not linear, and then we also discuss time invariance, that if a system response does not vary with time, whatever you get today, you're going to get the same thing tomorrow, is an example of a time invariant system. And then a few examples we considered, and then we came up with the most important mathematical formula of signal processing, which is convolution. That basically, if you assume a system is linear and time invariant, then h of n is very important, critical. H of n is the impulse response, and I said there's several problems in signal processing. One is the identification or estimation problem, the other one is the design problem, the third one is the analysis problem, the fourth one is the implementation problem. So all these problems revolve around h of n, because you need to come up with an h of n. Either you design, if you're designing your system, you are primarily designing an h of n, and if you are doing an estimation, you are estimating an h of n. And I gave you an example of MIMO system. It's a multi-input, multi-output system where you need to estimate so many of h. It becomes a matrix. Okay, so h of n is the basically it takes the central stage in signal processing, and just keep coming back to h of n, h of n. So h of n is the impulse response. And why we assume linear and time invariant system? Because if we assume linear and time invariant system, all we need to know about a system is its impulse response. That how system behaves if you input an impulse. Only if you know this much, that this is a system, if I input an impulse, what I get at the output. If I only know this much, then I can basically find out output of this system for any input. So that's why LTI is important. Linearity and time invariance is important, because linearity says no matter when you give an input, only move the output by the same amount. No matter how many inputs you give, so you add them together, you add the outputs together. Okay, if you shift the output. So linearity with time invariance basically helps you to come up with this h of n, which is so universal that just knowing this is enough to know everything about the system. Right? So that's why the LTI, the linearity and time invariance, these are two very critical properties of system. And usually, let me again emphasize that usually systems what we encounter in real life, they are not LTI systems, right? They are non-linear, they are non-linearity, they are dispersions, they are changing with time all the time, So though they are not, but we always try to model a problem which is non-linear in nature to make it linear for a small time duration. And you say, okay, this is piecewise linear, so let's not really worry about the non-linearity, let's make it linear, then solve it. And then you just keep solving it because of the inherent nature of the problem, that it is a non-linear problem. So we discussed that in detail, and we'll spend more time learning about that. But I mentioned that this is the most important and critical formula, and we'll spend today some time in learning more about this formula. So I said one interpretation of the formula is that you have a signal, you break it down into impulses, and we know that a signal basically is a summation of weighted shifted impulses. Then for every impulse you find out an output, assuming that you know the impulse response. So if you know the impulse response, so you are all done. So all you need to know is that, okay, if this is scaled by some amount, you scale this by the same amount. If it is shifted and scale, you shift the output and scale. So you shift the output and scale, shift the output and scale. And once you add all of these together, so you add all the inputs together, then you add all the outputs together, what you get is the answer to your question. That knowing the impulse response, if this is the input, then this is your output. Okay, so you have solved the convolution problem. So, and this is the order is not important. I did that last time, that if a change of variable will reveal that either you implement a system like this or this, both are equivalent. Mostly we implement a system like this. Okay, h of k, x of n minus k. Right? So means that
multiplication and add वाला.
जी.
अगर इस्तेमाल करें कोई रियल टाइम सिस्टम जिसमें काफी सारे सिग्नल्स हैं, तो हम काफी टाइम के लिए वो कर रहे हैं, मिलियन और बिलियन जो सैंपल्स इकट्ठे कर रहे हैं, तो इसमें तो फिर ये रियलाइजेबल ना होगा.
जी, मैंने ये कहा था कि that is not real. जी, that is not a practical way of applying the convolution. जी, that is not a practical way. I mentioned that last time as well, कि that is not a desirable way of solving the problem because of these issues. ठीक है? So we really don't use it. It's just for your understand. That is the easiest way to understand an LTI system. And it's basically that why it is useful. Somebody asked question why it is useful to implement a system as an LTI system. So the answer to that question is because of that and now the mathematical transformation. Right? So signal processing is about, I again mentioned in my first lecture that there's so many ways to implement a system. All are analytically equivalent, but they are different in implementation. So we then will try to choose a way which makes sense, which is more convenient. Okay, and which is obviously that you are implementing convolution. So analytically, we still want to go and implement a convolution summation. Okay. So then I mentioned about this, that this is a more desirable expression for convolution, and the reason is usually shortly we'll talk about finite impulse response and infinite impulse response systems, but that is primarily because if you open that up, it'll give you an expression like this: h0 x of n plus h of 1 x of n minus 1 plus h of 2 x of n minus 2. Okay, so let's say it has only three 3 coefficients of a system, then the equation will look like this. What is meant by this? That you are wherever n is your current position, that this is your current position and you are computing output for this particular value of n. For this value of n, you need to take x of n, which is the current sample, you need to take the previous sample, which is x of n minus 1, and you need to take previous to previous sample, which is n minus 2, and you consider h0, h1, h2. Sometimes I write indices like this, or otherwise the book follows this notation. Just to simplify my work, I just usually write it as a subscript, but both are same. They're not different, they are same. So this is the current index. So usually what happens is you get a current sample, you need to have 2 previous sample to compute an output. All you need to do is multiply this with this, this with this, this with this, add the answers together to get one output, and that will be your output at index n. So this is index n. So whatever output you get. Next time you consider the next sample. If you're considering the next sample, which is n plus 1, so this will move here, h0, h1 and h2. Similarly, you just keep moving the flipped version of the impulse response, one position to the right, and keep applying the equation. Right? So keep doing that, keep generating answers, and keep writing them down. This is the convolution equation. So we did this, and then I give you this example that this flip and basically this putting a mask and then moving it is not only valid for 1D signals, it is also valid for 2D signals. For 2D signals, for every computing one output sample, you need to do 9 multiplications and 8 additions. Then you move, then you compute, then you move, then you compute again. So this is valid for 2D or even 3D signals. Okay, there may be 3D signals, 2D signals, or whatever the dimensionality of a signal is, but your mask needs to be in that dimension as well. Right? So I covered this, that this is how you compute a value, replace it, and then I gave you several examples that the trick is in finding out the mask or the impulse response. That is the trick. Okay, these are just magic of numbers. Obviously there is no physical system as yet, as there is no physical system there, but the magic is in numbers, that the numbers you pick in a way that they give you the desired result. Right? And I give you several examples here. I'm just showing you an example which says the edge enhancement. So by just appropriately selecting those 9 numbers, you can almost get anything you want. Right? Same is the case in 1D signal processing, that by just appropriately selecting an edge, you can primarily get any kind of result. So we'll keep seeing this in this course. Then I showed you that in a 1D signal, this is your input, this is the index n, this is your input samples, and this is your impulse response. So you write it in a reverse order, and then just keep moving it and keep multiplying and adding, and that will give you the final answer. G. Agar if you are convolving impulse response is given, there is a problem which is called blind deconvolution problem, where you know the input, you know the output, we don't know the impulse response, and you get these type of questions in exam as well. So you know the input and output, how do you find out h of n? Okay, obviously you try to figure out the formula. That formula says now h0, h1, h2, they all are unknown. You know x of n, you know y of n, and this is very true in seismic signal processing, where they are figuring out the presence of oil or natural resources. What they do, that they send an input, basically they blast something, and then they get the reflection. So reflections are basically the output of a system, and what they induce is the input. So from that they try to figure out the system, and they know if there is some oil reserves or gas reserves, the system will behave differently. So by knowing the input and output, they figure out the impulse response, and then impulse response basically tells them whether there is something under the ground or not. So this is, if you don't know the impulse response, again it is an identification problem. And how do you figure out? You give a known input, you get a known output. It's a difficult problem, it's not an easy problem to solve. Let me tell you this, it's a difficult problem to solve, several reasons, but you give an input, and that's what we do in communication as well. In digital communication, you send a known signal, a known preamble, which is known to the receiver. Now you are sending something, the receiver knows that you are supposed to send this, okay, but it will get something else. Knowing what has been transmitted, it will try to figure out the channel. So this is again a problem which a communication receiver is always solving all the time. Whenever you turn a receiver on, it is solving this problem for you, okay? And it got to solve it, only then you really hear what you hear. So this we covered. This is kind of where we left, that if you are asked to convolve, one easy way is, let's say, if you are asked to convolve this signal with itself. It is 1, 1, 1, 1, 1 from 0 to 5. So one way is you write 1, 2, 3, 4, 5, 6 ones, and then you write 6 ones here. First you start from here, 1, 2, 3, 4, 5, 6, okay? So 1 into 1 is 1. Then you move 1, 1, 1, 1, 1, 1. 1 into 1, 1 into 1. 2, add them together, 2. Then you move 1, 1, 1. So you are moving this every time to the right by one position. Every time you multiply and add. So first time you will get 1, second time you will get 2, then you get 3, then you get 4, then you get 5, then you get 6. 6 is once you have, we call this a full overlap. 1, 2, 3, 4, 5, 6. So this is a full overlap. Right? And now once you move, you again are getting out of the signal, so you get partial overlap. Right? So partial overlap is again you get 5, then 4, then 3, then 2, then 1. So this is what you get. Okay, so this is the output of the convolution. And let me also remind you that in real life, you will never be asked to convolve two things which are finite. Usually your signal is infinite. As soon as you turn on your system, you keep getting your input signal. Maybe for days, maybe years, maybe months. Okay. So the input signal is usually a signal which just keeps on running. Okay, it never ends. If system is on, it is on. So you're continuously sampling the signal. Right? It is just the impulse response which is finite in many cases. If it is finite, जी. जी जी बिल्कुल नहीं उसकी फाइनाइट नहीं होती. आई नेवर सेड दिस. ओके नहीं, द क्वेश्चन इज द इनपुट डेटा फाइनाइट? आंसर इज नो, इनपुट डेटा इज नॉट फाइनाइट. ठीक है, इनपुट डेटा इज नॉट फाइनाइट. द रीजन इज दैट वंस यू जी जी बिल्कुल नहीं उसकी फाइनाइट नहीं होती. आई नेवर सेड दिस. ओके नहीं, द क्वेश्चन इज द इनपुट डेटा फाइनाइट? आंसर इज नो, इनपुट डेटा इज नॉट फाइनाइट. ठीक है, इनपुट डेटा इज नॉट फाइनाइट. द रीजन इज दैट वंस यू टर्न ऑन योर सिस्टम, ठीक है, यू स्टार्ट एक्वायरिंग डेटा. लेट्स से आपने सैटेलाइट पे भेज दिया कोई चीज, इट विल बी इन ऑपरेशन फॉर 10 years एंड यू आर सैम्पलिंग एट 10 मेगा सैंपल्स.
कंटिन्यूस टाइम सिग्नल होता है सर, उसे डिस्क्रीट टाइम में कन्वर्ट करने के लिए सर आप एक अमाउंट ऑफ डाटा सेलेक्ट करते हैं. सर कंटिन्यूस टाइम तो इनफाइनाइट होगा, लेकिन जिसके ऊपर पर्टिकुलर
नहीं आई थिंक now you are confusing two things too. ठीक है, a continuous time signal is you sample a continuous time signal. ठीक है, so this is where on a discrete interval in time you go and read a value. ठीक है, this is that you at discrete interval in time, but how many times you go it is infinite. Okay? How many times you go it is infinite. But why? Because if system is on all the time, it is infinite. You can put sample. So we'll keep coming back to this. तो बताने का मकसद ये था कि once you have a signal, okay, if this is your signal and you start convolving, initial samples will be garbage samples. Okay, because there is no full overlap. First only one sample, 2 sample, but 5 sample worth of garbage is nothing because system will be on for so many days. So 5 samples you throw away, and then 5 sample, there is only one valid sample in this example once you have full overlap. In this particular example where you are convolving 5 samples with 5 samples, there is only one valid samples, and that is once there is a full overlap. Okay, and then again you have partial overlap, that is again garbage. So garbage and garbage, initially you get few samples which has partial overlap, then you get few samples which has partial overlap. Usually we throw away these samples. Okay, my valid samples are once I have full overlap, and that full overlap will remain as long as the system is alive. That is important. Just 5 samples worth of data once you are sampling at few megahertz is nothing, it's few nanoseconds, so you don't care. Okay? That's what I really want to point this out here. So coming back, but we need to learn the mathematics, and that's why these small examples are given, that you just go do some exercises to know that, okay, this is how you basically convolve two signals. Okay, this is where you have a signal and you are just bringing it, and then you are just moving it, and then you get out of it. This is another example that you are convolving this signal with this signal. Okay, so if you are convolving this signal, let's say 1, 2, 3 with signal 3, 2, 1. Let's say you are asked to convolve this signal. So you need to flip one. Okay, you keep this as is. So this is 1, 2, 3. One ways you write 1, 2, 3, and 3 to 1 you write 3 to 1 like this. So one write on this from going from right to left, and one signal you write going from left to right, and then just keep moving this every time. 3 ones the 3. So once first sample is 3. Okay, then you move this one 3, 2, 1. 3 2's the 6, 2 1's the 2. 6 plus 2 8. So you write 8. Then you have 3, 2, 1. So 9 plus 4 plus 1, 14. So you write 14. Okay. So then again 1, 2, 3, 6 and 2, 8, and then finally 1, which is 3. So this is what you get at the output.
So why do you flip it when you know that there will be partial?
Because of the formula. Remember, I showed you the formula which says x of n, h of 0 plus x of n minus 1, h of 1 plus h of 2, x of n minus 2. So once n is 0, so only you get x of 0, h of 0, because x of minus 1 is not there. You are starting at 0 time, there is nothing at minus 1, minus 2, minus 3 indices. Once you turn on the system, that time is your 0. There is nothing in the negative time axis. So because the formula says that so usually once your question is valid, that once we are implementing a system, we don't do partial overlaps. We start at n is equal to 2, because I know I'm going to get a partial overlap at 0, 1. So I really need not to compute it. And that's what we do in image processing as well, because once you are on edges, you have partial overlap. That mask on edges is not full it's a partial overlap. It's not full overlap. So you don't compute edges. Edges will be corrupted. So you just compute, and you have to throw away the edges. So the image size will reduce. So then you can just copy the same. There's several ways people handle this problem. But remember that there will be a partial overlap problem in images as well, because once you are moving on the edges, you don't get full overlap. Okay? So this is yet another example, but the example I really want to do is, so this is the answer to that problem. This is just to demonstrate that in 1D signal processing, usually you are encountering noise. So this is a noisy signal, it's the original signal, a voice, and you can just imagine that it's just nothing but noise. So the magic of signal processing can clean this signal and will give you back your original signal. So this is why signal processing is used, that using signal processing somehow you can remove noise from a signal, and several other reasons that why you do signal processing, which will keep it depends. Sometimes you can completely remove noise, sometimes you can reduce noise. Precisely, you cannot do that. But if it is an out of band noise, okay, your signal is in this band and there is noise in this band, okay, so you can remove by using a good frequency selective filter. You can almost completely remove this noise, which is out of band noise. If it is an in band noise, then you need to know the noise model, the statistics of the noise, and then you can counter that. Okay? So we'll come to that, but if it is in band noise, obviously you can reduce the noise, and then you must be knowing in CDMA and all these things, even it is an in band noise, but still you can easily remove it. So ways. Okay, so image in 2D convolution, the same formula but involving two summations. This is the mask and this is your image. Right? So I really don't want you to worry about it, but I'm just mentioning it to let you know that image processing and signal processing, they both are just same. It's just that you are now the original was, for example, the convolution, you write h of k x of n minus k summation k goes from minus infinity to infinity. If it is 2D, you write k1, k2, n minus n1 minus k1, n2 minus k2, and write another summation. This is on k1, this is on k2. And at the output you get y of n1 comma n2. Okay, so n1 n2 is the index in an image. So this is your mask. H k1 k2 is your mask, and this is the image. So you are just moving the mask over the image. Okay. So, and same is true for 3D as well, that you can just keep putting as many summations as you want. Just keep adding k1, k2, k3, k4, because all happening in your computer. So you can have a signal which is a 3D signal or 4D signal or 5D signal. It may not have anything to reality, but you can always have these things. So this we have already seen. Same. Now this is really the problem which I want to solve, and this you really need to understand too, because this is a very classic problem, convolution, and people usually don't understand this. So let's say this is an h of n, a signal which is 1 from 0 to capital N minus 1. Capital N could be anything. Okay, so it is 1 1 1 1 1 and then n minus 1. This is my, let's say, impulse response. Okay. Then I have another signal which is, let's say it is my x of n, which is a n u of n. Okay, so this is my x of n. Now the formula, so we can use one of the two formulas, but is yet another interpretation of convolution, which has perhaps no practical significance but a lot theoretical significance. Usually, and once you are actually implementing, you really don't worry about these things, but from theory perspective you need to really know this, that you are now applying a formula which says x of k, let's say h of n minus k. So the two formulas, you can use either one of the two. K goes from minus infinity to infinity is equal to y of n. Now this is usually called a graphical way of solving convolution. It's also called flip and drag method of solving convolution. But what the formula tells us here is that I need to solve a summation which is running over a variable k. Okay? A summation which is running over variable k. So for this, the variable of summation is k. Anything which is not k for this summation is a constant. Right? So for this summation, n is a constant. Okay. But for this equation, n is a variable. Means you need to solve this summation for different values of n. You put n is equal to 0, you solve the summation. Means that for computing one output value, you have to solve the summation. So this is signal processing, that you have to pay. To get an output sample, solve the summation. If you want to solve it for n is equal to 0, okay, put n is equal to 0, solve the summation. If you want to solve it for n is equal to 100, put n is equal to 100, but solve the summation. So go back, solve the entire thing, you will get just one value out of the summation. So end of the day, you do all the multiplication, additions, you get a value, that is your output. Okay? Then you change n, you change n, you change n, keep doing this and keep solving this, and you get just one value, one value. So computationally it is intensive, we say. It is intensive because you are solving a summation for every value of n. And now look, let's think of it in a graphical manner, that if I am solving this summation, I need to have a signal x of k, okay, and I need to have a signal h n minus k where n is a constant. Okay, let's start with some negative value of n. You say, let me solve this for n is equal to minus 1, for example. N is equal to minus 1. I want to first solve it for n is equal to minus 1 to see what will I get. Okay, so for that I need to plot x of k graphically to see what is happening. I need to plot a signal which is x of k, and I need to plot a signal which is h of minus 1 minus k. Then I need to do multiplication. What type of multiplication? Point by point multiplication. That's why I just revise everything, because it's a mathematical operation on signals which says on sample by sample basis. So you plot x of k, you plot h of minus 1 minus k, and then you do sample by sample multiplications, and then summation says add all the values what you get after multiplying the signal on sample by sample basis, you will get one value, and that will be your output. Okay, so let's do this exercise. Let's first plot x of k. I know x of n is this, okay, which is a n u of n. A is any number 0.8, 0.9, so it's a decreasing exponential starting from a, then this is n. For n is equal to 1, it is a. For n is equal to 2, it is a square, a cube. So if a is less than 1, it will exponentially decay. If a is greater than 1, it will expand. So now if I intend to plot x of k, all I need to do is replace n by k. Okay, this will become x of k, and this was originally an n index. I'll make it a k. So it's simple. So plotting x of k is simple. Okay, now plotting h of -1 minus k is not that simple. So we'll see how. So h of -1 minus k. To plot this, first let us plot h of k. Then let's do h of minus k. Then do let's h of -1 minus k. So what is h of k? Same signal, just instead of n you write k. So this is h of k. So this is simple. H of k is simple. What is h of minus k? That is the flipped version, because minus k means that once you put k negative, only then you get h of bracket positive, which is defined. So h of minus k is same signal flipped in time. So if it will go from 0 to minus n minus 1. So if n minus 1 is 5, it will go from 0 to minus 5. So it will go in this direction. So this is h of minus k. Okay, so h of minus k. And then what is h of -1 minus k? So you say let's find out where the 0 is. So how to find out where the 0 is? Put this equal to 0. So k is equal to -1. So this is a signal, the same signal shifted to -1. Okay, so the same signal shifted to -1. So instead of this, it will be shifted to -1, -1. Okay.
Minus common
जी हाँ,
minus k minus.
ये भी कर सकते हैं. h of minus into k plus 1. -1 लेंगे तो 1 plus k आएगा जी. But this is just a better way that you first flip and then figure out where the signal will be. ठीक है. अच्छा, this is at -1 signal. If it was originally from, let's say it was from 0 to 5, first it will go from 0 to -5, then once you shift, it will go from -5, -1 to -6. Okay, this is what it says. Now you need to do sample by sample multiplication. Remember, the operation says sample by sample multiplication. Right? And this is really the most complex concept in engineering, the convolution. Okay, why? Because of all these variables are involved. So -1, you plot it. So you say, okay, plot this signal which runs from -1 to -n -1 -1. So now you do sample by sample multiplication. So what do you get? 0. Okay. Again, let me repeat. We are trying to solve the summation using a graphical method. For solving this summation, I need to solve it for different values of n. I need to plot this, I need to plot this, I need to do sample by sample multiplication. So whatever I get, I need to add it to get one value. I am considering n is equal to -1. Once I say n is equal to -1, I plot x of k, which is this. I plot h of -1 minus k, which is this. Now I do sample by sample multiplication. I get 0, so 0. My answer is 0. So for y of -1, answer is 0. What will be y of -2? Again 0, because no matter where you move it, this is -1 is really n. Okay, so -1 is really n. This is important, that -1 is really n. If n is negative, you remain on this side. This signal will remain on this side. Okay. So if you plot this h of n minus k, you first flip, you plot h of minus k. Then I ask you to plot h of n minus k. You say h of n minus k is equal to 0. So k is equal to n. So this signal is really, this is your n and this is minus n minus 1 plus n. If n is negative, this n negative means you will never overlap. So there will be no overlap. So we, instead of just computing for minus 2, for minus 3, for minus 4, for minus 6, I simply say that once n, this n is away from the 0. If n is less than 0, so I say if n is less than 0, y of n will be 0. There will be no output. Okay, for negative indices of n, there will be no output. Graphically, it tells me that there will be no output once n is less than 0. So now what happens is, once n becomes equals to 1 or 0, so once n is 0, you are here. 0, 1, 2, minus n minus 1. Okay? This is the first time you will get an output value. Once n is equal to 0, you will get an output value. Okay, so this is 1 into 1 is 1. So first time you are going to see an output is at 0 and the output value will be equal to 1. Second time, once n is equal to 1, what will happen? So when n is equal to 1, this will come here. So what will be the answer? How many samples are overlapping? 2. So what is the answer? Do sample by sample multiplication. 1 plus a. Because 1 into 1 is 1. 1 into a is a. So 1 plus a is 1 plus a. So next sample will be 1 plus a. Okay. So then the third sample. So what is the third one? 1 plus a square. Right? Because now 3 samples are overlapping. So you keep dragging. This is your n. N is equal to 2. So for every value of n, this is minus n minus 1 plus n. Okay. So here the 3 samples are overlapping. So you get 1 plus a square. Okay. Then you again move 1 plus a square plus a cube. So these are your output. So the outputs will just keep going up, and a time will come once you will have full overlap. That is the time once you are going to see a value, and then it will get into the full overlap. It will keep getting full overlap. Acha. So here we can safely say that the first time I am going to see a full overlap is when this thing will become equal. This is the first time I'll see a full overlap. Okay, and then you keep seeing full overlap. Okay? So minus n minus 1 plus n. So and you must have done this convolution, and that's really the prerequisite to this course, that you must have a fairly good understanding of convolution. If not, please go back, do this again and again and again. Maybe you may spend, just do it 10 times, but really need to understand this. So minus n minus 1 plus n, once first time you hit 0, this is the time you are going to see a full overlap, because this tail will be here. So here you can find out what is n. N will be n minus 1. So the first time you see a full overlap. Okay. Until if it is n is less than n minus 1, you keep seeing the partial overlap. Okay. And once it is greater than equal to 0. So if this tail gets to 0 or 1 or 2 or 3, so if this tail is 0 or positive values, you keep seeing full overlap. Okay. So what we do is we divide in convolution, in graphical convolution, we divide the problem usually in three areas. Once there is no overlap, then there is full overlap, then there is partial overlap. Okay, so first is once you have no overlap. No overlap is once your n, which is this, is less than 0. So y of n will be 0. Then there is partial overlap, and it is when n is less than n minus 1. Once there is a partial overlap, so to make a closed form expression for all the outputs you get in a partial overlap, this is the situation that you have a partial overlap. This sample is n, this sample is n minus, I'm just writing n on this side, it really does not hurt. देखिए, अब this is the case of partial overlap. ठीक है, I'm saying this n minus 1 is still away from this 0. So really the effective values I get is from 0 to n. Okay? Once I do a sample by sample multiplication, I'm really multiplying these values with these values. So all these zeros multiplied by non-zeros will give me zeros. So it will not affect the summation. So I can, in a closed form, I can write the expression as y of n is equal to k, and remember this axis is k. K going from 0 to n. And what is my x of k? X of k is a of k. So this is my x of k. So x of k, I can write it here. X of k is a of k and u of k. And what is my h of n minus k? For every sample it is 1, because 1, 1, 1, 1, 1, no matter what. So this is what I need to solve. This summation, k goes from 0 to n, a of k multiplied by 1. Okay, and this, if I solve this summation, there is a formula which says alpha of n. So the formula says if you are solving alpha of k, or k goes from 0 to n, the answer is 1 minus alpha n plus 1 over 1 minus alpha. So this is the formula, right? This is summation of series formula from your FSC book, high school books. If you have a geometric progression, then this is the summation. Okay, this is the answer. If you are adding all the values, you will get this answer. Okay, so for this you will get an answer which is equal to 1 minus a n plus 1 over 1 minus a. Okay, this is your answer for partial overlap. Once you hit, first time you hit 0 and you are less than n minus 1. This is the first time you hit 0. For example, if you put n is equal to 0, what do you get? 1 minus a divided by 1 minus a. 1 minus a divided by 1 minus a is what? 1. So it is the first output sample you got, and remember the first was a, 1. The second was 1 plus a, and we can figure that out from here as well, because it is 1 minus a square divided by 1 minus a. 1 minus a square is 1 minus a, 1 plus a. So 1 minus a will cancel out of 1 plus a. So basically this gives you, this is not one answer, okay? This is not an answer. This gives you a closed form expression for all the output values you will get until this n, the index runs from 0 to n minus 1. It only tells you this. Okay, this is, so you put a value of n, it will give you an answer, you plot that answer. So this is not one value. This is a closed form expression for all the answers, okay, which you get once you are moving in a partial overlap region. And then comes the full overlap. Okay, now let's do that. So the full overlap, let me plot it for you to really understand it. So partial overlap is this is 1 a square, a cube, it keeps going like this. This is k, this is x of k, which is equal to a of k, u of k. And here is your somewhere from n to n minus 1. Now it is away from 0. This tail is away from 0. Okay, and I'll just keep going on and on because it's an infinite signal. Okay, so once you have a full overlap, once n is greater than equal to n minus 1. Okay, if n is 5, then once you get n is greater than equal to 4, you start getting full overlap. I'll do this in MATLAB as well for you to really understand and spend a lot of time in understanding this. This is the core basic concept. You really need to know this. Okay, so now the full overlap, you are multiplying. Now equation says that you need to multiply these two signals together. So the equation says that you have an x of k, h of n minus k, k goes from minus infinity to infinity. This is the summation. Okay, so let's multiply. If you multiply this with this, so you need not to worry about these values. Why? Because all zeros. You need not to worry about the values beyond n because all zeros. So the summation, instead of this is a k axis, it says run the summation from minus infinity to infinity. You are saying no, it is not required. I can really run it from this value to this value because this is only non-zero. Once you're multiplying two things, what matters is where the values are non-zero. Otherwise 0 multiplied by something is 0. So you say I will run it from n minus 1 to n. So you modify the summation as you do in integration because this is the valid limits for the summation and this is where you get non-zero values. So okay, this equation will run only for these values. Now write what is x of k. X of k is a of k. U of k has already been catered here because it says only positive values in Shoab on this side. So a of k and h of n minus k is always 1. Otherwise you have to write h of n minus k as well. Okay, because 1. So you write a of k and there you write 1. So all ones. In this range, h of k is 1 for every value of k. Okay. So now you apply a formula, okay, which says if you have k going from n1 to n2, so there is a formula alpha of k. Okay, so you apply that formula to get the final value. जी नहीं, h of n minus k की जगह u of k नहीं, h of n minus k is 1. ठीक है ना, because it is 1, that's why I'm just writing 1. U of k तो is only says that it is on the positive side, so you already know it has been catered for in the summation because summation is inside beyond 0. ठीक है, so it has been catered there. So this is so this is shown here that you on k axis, okay, you keep one signal as is. It's up to you because it works in both ways. So you keep one signal as is. Let's say you have chosen to keep x of k as is. Keep x of k as is. So this is your x of k. Flip the other signal. Find h of minus k, then shift for negative values of n. So this n start from here. And remember, this is on the same k axis. So n here means that it is on this side of 0. It is a negative value of n. So you can, by just looking at these two signals, you can safely say that until this n hits this 0, you keep getting zeros at the output. There is no overlap. Okay, so safely you say this, that y of n is 0 for n is less than 0. Okay, then comes a point where this n, so you are basically dragging it. So you just keep dragging it, and the time once you first hit 0 is the first value you get at the output, and then you are here. Once, though n is away from 0, but n minus 1 is still on this side of 0. You can easily figure out for what values of n this will hold good. Okay, how you say n minus 1 is less than equal to 0, I get partial overlap. From here you find the value of n, which says this is the value of n. N is less than 0 and n is greater than equal to, for partial overlap, n is greater than 0 and n is less than n minus 1. You keep getting partial overlaps. Okay, so the summation will run where there is an overlap, and the overlap is from 0 to n. So 0 to n there is an overlap, a of k, and you use the formula 1 minus a n plus 1 over 1 minus a. This is the answer. Again, it's not one answer, it's not one value. This is a cumulative, a closed form expression for all the values you get for these ranges of n. Just keep putting values of n, you will get an output, an output, an output, an output, an output. For let's say n is equal to 10. So this will hold good from 0 to 9. So first put 0 here, plot a value, put 1, plot a value. And obviously using a computer you are not interested in closed form expression. That's why I said this has no practical significance. This has a great theoretical significance, that usually you really need to know this, but no practical significance. G.
If you have finite signal, you have two partial overlaps.
G. If you have, let's say there is a problem which I'll be giving you as an assignment. It's a finite signal here and a finite signal here. Okay, so then what will happen? So once you plot this, so this let's say is running from 0 to n1, and it is running from 0 to n2, where n2 is greater than n1. Okay, so first you plot it, flip it, plot it here. Let me plot it with some other. The question is, what if both signals are finite? So you plot this one here. So this is your n, okay, and this is n minus n1. So until n is away from 0, there is no overlap. And then a time will come, once you just moving, you will come here. At this point there is a, and this partial overlap is, right, once the n though is greater than 0, but n minus n1 is less than 0, you keep getting partial overlap. Then a time will come, once you have a complete overlap. So when will that happen? Again, very easy to figure out. This is n, this is n minus n1, this is n2, this is 0. So the partial overlap will happen once this edge is away from 0, but this edge has not crossed n2. So you put like n minus n1 needs to be greater than equal to 0, and n should be less than n2. So this is how you find the limit. And you say, okay, n is greater than equal to n1 and n is less than n2. So you can write it like this: n is less than n2 but greater than equal to n1. This is how you write limits. In this region it will have a complete overlap. Then what will happen? So you keep moving this on, okay, and this is again partial overlap. This is n and this is n minus n1. So when will it happen? Once your n crosses n2 and n minus n1 is still away from n2. So again you can easily figure out the limits. You say, okay, once n goes beyond greater than equal to n2, n goes away, you will get same answer. ठीक है, जो ये point है where you get last time you get a full overlap, you will get same answer in both cases. It's guaranteed. Okay, so you can say n is greater than n2 to be exact, that this is a partial overlap, n is greater than n2 and n minus n1 is less than n2. Okay, so, or you can say less than equal to, because last time you are going to see a partial overlap once you are on n2. So you say n is less than n1 plus n2. Interesting is what we'll ask you to do is just put a real values of n1 and n2. So you will see an output which is a partial overlap, then full overlap, then partial overlap, and then zeros. So this is where n is greater than equal to n1 plus n2 and still less than something. N is greater than n2 and less than this, sorry. N is less than this and greater than n2. Okay? This is again gives you partial overlap. And when there will be no overlap, so once you are here, this is n2, this is n, this is n minus n1. So you say once n minus n1 is greater than n2, there is no overlap. Right? This last time you see an overlap is once you are on n2. So you go out. So n is greater than equal to n1 plus n2, there is no overlap. So no overlap, then partial overlap, then full overlap, then partial overlap, and then no overlap. Okay? So this is what you will find out. That interesting is an example. Let's try to figure out what will happen. If I ask you, you have all ones going from 0 to 99, okay, and you have all ones going from 0 to 9. Let's try to guess. Okay, there will be no overlap once. Now once you flip it, it will be like this. This is n and this is n minus 9. Once n is away from 0, there will be no overlap. So first time you see an overlap is once you are at 0. So you see an overlap, you get 1. Then another overlap, you get 2. Then you get 3, then you get 4, then you get 5, then you get 6, you get 7, you get 8, you get 9, and you get 10. When are you going to see 10? Once you are at 9. Okay, 0 pay 1, then 2, then 3, then 4. And this is where you have a complete overlap here. 1, 2, 3, and this is. Once you are at 9, you have a complete overlap. Then you keep seeing complete overlap till what point? Once this is, remember, this is your n. N is 99. You are going to see a complete overlap. And what is the value of this complete overlap? 10. What will happen once you hit 100? You get partial overlap, partial overlap, partial overlap. When is the last time you are going to see an overlap? Once this n minus 9 is equal to 99. So actually compute n minus 9 is equal to 99, mean n is equal to 99 plus 9, which is equal to 108. So at 108 you are going to see the last overlap. So interestingly, by just looking at the formulas and everything, your signal always starts from this plus this, and it always ends from this plus this. Always. No matter what these indices are, your signal starts at this plus this, and it ends this plus this. Okay? So we'll start 0 plus 0, will start from 0. And this plus this will end here. If it is minus 10, it will start at minus 10. If you are confusing the indices, it's better that you bring both of them at 0. If I give you a question and I put this at starting from minus 100 and going to, let's say, starting at 100 going to 1000, and this one starting at minus 20 and going to minus 40, and I ask you to convolve them, it will be difficult for you to do all the math like flip, drag, and find the indices. One way is you move both of them to 0. Both are starting from 0. Find the answer. Then the final answer will start at what value? 100 minus 40 will start at 60. Where will it end? 1000 minus 20 will end there. So you just move it. and you'll get the answer. Right? Another, because of this, if length of this signal is L and this signal is M, then length of the output will always be L plus M minus 1. Right? So the output will give you more samples, and remember, most of these samples are garbage. Some of these samples are garbage, because you put M samples, you want M samples out, because it's just a system. So a lot of garbage samples. Usually you throw away the garbage sample. What MATLAB usually gives you is the same amount of samples what you put in. So we'll keep rest of the sample, throw away rest of the samples. It'll give you the same amount of samples. Okay, filter command in MATLAB. So coming back to this, is again, you really need to go back and practice it. We'll give you an assignment also, and we'll give you MATLAB assignment, we'll give you a theoretical assignment to work on these problems. Now, okay, so this is the answer. It is the formula is, this is alpha 1 minus a alpha 2 plus 1 and 1 minus alpha. So the formula for if you have a summation to solve which is running from n1 to n2, there is an alpha of k, so you get alpha of n1 minus alpha of n2 plus 1 over 1 minus alpha. This is the answer. Okay, so this is the formula. So you just apply the formula, you get the answer. But interesting is the output. Okay, for some value of n, once you get a partial overlap, you are going to build up the output will always increasing, starting from 1 plus a square, 1 plus a square, 1 plus a square, 1 plus a square plus a cube, 1 plus a square plus a cube plus a4. You keep building that. This is the last time you are going to see a partial overlap. Then you have a full overlap, because you are moving and the summation of these values, they are decreasing, because once you are here, you will get a bigger value. As you are moving, because these values are reducing, that's why you will. So the effect of applying this to this is that it will remove this edge. It will smooth the signal out, so to say. Okay, because it's zero and starting and then it's just dying. What this will do is it'll make it grow and then it dies. If you consider zeros are also valid, that it is a signal which is zero, then all of a sudden it starts and then it dies. So the effect of this filter is to smooth out the signal. Okay. So this is from my original notes once I took this course at Georgia Tech. So this gives you all these scenarios. Just go back and figure out yourself, because here it's saying this plus this. So here the signal is running from here to here, here to here. So you flip. And I have already run all the scenarios. So you say, okay, once you are away, there is no overlap. I'll say for these values of n, there is no overlap. Then there is a partial overlap. Then is a full overlap. Then there is a partial overlap. Then there is a no overlap. Right? And these are the ranges. It computes all the ranges. The only difference is it is assuming the signal is starting at NF1, not from 0, NG1. So once you flip, it is G. So it is N minus NG1, and this is N minus NG2. So this is N minus NG1 is away from NF1, not 0. So this is the only difference. N minus NG1 is less than NF1, you start, there is no overlap. Right? So you just need to say that this is N minus NG1 and this is N minus, and that's it. Rest everything is same. You say until this is away from this, less than this, there is no overlap. So this is how you say it. N minus NG1 is less than this, so you are away. Once this is inside greater than this, but this is less than this, there is a partial overlap. Then once this is greater than this and this is less than this, there is a again partial overlap. There will be no overlap once this one is greater than this, and there is no overlap. So just all it covers a slide and It's also got flip and slide method. It'll cover everything for you.
So for a constant signal that the signal time turns zero after a while, we will say that the signal is finite.
G. A signal is finite if it.
Even for a like for example, the signal we consider a raised to power k. When k becomes increasingly large, the signal will.
No, that is an infinite signal. A raised to the power k is an infinite signal. Why? Because it is not becoming zero. A k u of k is an infinite signal. The reason is that no matter what value of k you have, there will be a value. It will be very small. The value is going to be there. So this is an example of an infinite signal. Finite is only if I say n only runs from 0 to 100. Okay. Now it is a finite signal because I am saying just cut it from 0 to. This is a finite signal. Okay. Because I am saying that this is what the signal is. Azan. Now in reality, once we are saying we are implementing a system, nothing but it's lot of systems there. It's just cascade of systems. For example, remember, system means anything which processes your signal, whether you are doing it, whether your electronic circuitry is doing something to your signal. As somebody mentioned, there is noise which is being added by your electronics. Okay, so everything which is doing anything to your signal is basically a system, and usually it's a cascade of systems which are there. That a system. For example, a transmitter is a system. Okay, it goes through air is a system. It comes back to your receiver is a system. Okay, so all these are systems cascaded together to form a bigger system. Sometimes they are parallel systems. So a system, especially once you have, let's say, multiple antennas and you have space diversity, you have multiple antennas, and as what I showed you earlier, so this is a system, this is a system, this is a system. They are parallel systems. Okay, so you are a system here, system here, system here. These are the parallel systems. You may have same input going through several parallel systems. If they are linear and time invariant, this is important, and this is why linearity and time invariance is important. That if whether you put them in cascade or you put them in parallel, if they are parallels, if they are linear and time invariant system, you can do the math. The math says that the order does not matter. In which order you put these systems together, it does not matter. If this is an input, this is an output. If you put theoretically put air first and transmitter after that, you are going to get the same output. Okay, if you put the receiver on this side and air on this side, you are again going to get the same thing. Okay, no matter in which order you put. If they are linear and time invariant, order does not matter. Okay, so order does not matter if the systems are linear and time invariant. Again, mathematically, I'll not get into the math. Mathematically, the order does not matter, and this is important. That in some cases, very important. That a system basically is, and there is more to it. One is the order does not matter. If impulse response of this system is h1 of n, impulse response of this system is h2 of n, impulse response of this system is h3 of n. These all are systems, either you have designed them yourself or they are just there by virtue of being there. The order in which they are connected together does not matter. Okay, number one. So this is one result. The math says it. If they are linear and time invariant, math says it. G?
Satisfies associativity.
G, associativity. Okay. The important is that to compute the output, what do you need to do? Let's say this is the input, x of n. Obviously, you say, I know to get an output here, I need to convolve. This is the notation which we use for convolution. You say, to get an output here, I'll convolve this impulse response with the input, putting that equation. Okay, so this is what you get here. So then there is another system. You say, okay, I'll again convolve. So this is the output here, right? So what do you do then? Say, okay, then I again convolve. This is the output. I get the output here, which is my output, by the way. Okay? Lot of brackets. So say input, convolve, whatever you get, convolve, whatever you get, convolve, whatever you get, convolve. Okay? It means if I just, brackets are not really adding any value. I say really let's not worry about brackets. Let me put brackets here. And this is a very important result in signal processing. It says if you have so many systems cascaded together, you can know their impulse response. You can convolve them together, knowing this flip and drag and get a value, all that. So put all of them together, a consolidated system H of n. Okay? So instead of convolving, doing 3 convolution, you first find an overall system and only do 1 convolution. Okay? So this is a very important result in signal processing, that just number of systems cascaded together, so you can put them together and just use 1 system. But interestingly, in signal processing you will find people doing otherwise. Let's say if I want to have a system, I can really break it down into multiple systems, and instead of implementing 1 system, I'll multiply 3 systems because it is equivalent. Why would I ever do this? In several reasons. We'll keep coming back to this. In fact, we recently published a journal paper on this, that how can you effectively design things which are almost impossible to design. And I'll cover that once we come to that section, that you just disintegrate it. You say, oh, these are so many systems, you divide and you say, okay, cumulatively this is the same system. Though a system, while implementing H of n, there may be things which are not possible, but if you divide them, so divide and conquer, you say, okay, I'll divide them and now the things are possible. So this is a very important result. Same is here. If you have a system H1 of n, in parallel you have another system H2 of n, another system H3 of n, and here is your X of n. So basically you need to convolve it with this one, you convolve it with this one, you convolve it with this one, and then you add. Because addition is also obeys linearity. Okay, so instead of just doing the individual convolution, H1 of n, then you have here xn into H2 of n, then you are here xn into H3 of n. What you can do is you are adding them together. So you are saying this plus this is my output. So you take x of n common and you say H1 of n convolve with H1 of n plus H2 of n plus H3 of n, and this is on sample by sample basis. That if you have systems in parallel, add their corresponding samples to get just 1 system. So instead of putting, there are 4 systems in parallel, you can implement it as a 1 system, and again you do it otherwise. In practice, you use this to disintegrate a complex system into number of systems. You say, okay, this is a system, let me divide it into 10 or 5 or as many systems as you want to divide, because you know that you can always do that. And once, all you need to make sure that once you add all the samples together, you must get H of n. Okay? That's all you need to ensure. So these are 2 very important properties of system, that it says that you can distributive and associativity जो है वो जी yes, you can do that for the duration, for a time duration. You say, okay, this system is adaptive, means that it's only valid for a small time duration. Okay? After that you need to recompute the coefficients. So for that much time duration, obviously you do that. Okay? So this is what it says, that it obeys associativity and distributive properties of maths, that any order does not matter, and importantly that it's not the order which does not matter, you can put them together as 1 system and vice versa. And if they are parallel, you can just put 1 system, adding the corresponding samples together, and otherwise that you can break it down. That's what we will use, that there is a system, you'll break it down into several systems which are parallel or otherwise. Let me just cover this slide and then we'll take off. इससे स्टेबिलिटी. अच्छा, अब होता ये है whether it's a though it is a linear and time invariant system, ठीक है, whether it is an analog system or a discrete system, stability is an issue. Stability means के you give a bounded, a valid input and it start giving you infinity at the output. एकदम से ऊपर गया और saturate हो गया, you know. So that is something which you say, oh, this system is not stable. As for some reason it is giving you something which you really don't want. So the definition of stability is that if I give a sample which is valid, all the samples are valid, mean they all are finite samples, I want my system to give me finite value at the output. Okay? The legal input, it should give me legal output. So we call this a bounded input, bounded output stable system. That if an input is bounded, so for any value of n, if the absolute value of any sample is always less than a finite number L of x, I want my system to give me a valid answer at the output. This may seem very simple, but you really have to ensure that your system will give you that. Otherwise, if you really don't worry about it, it'll give you infinity. Very soon it'll just saturate, it'll start giving you values which are larger than whatever this value is. It's a very simple mathematical validation of the stability rule, and the stability says a system is stable that if you add all the samples in its impulse response, take the absolute of all the samples in the impulse response, if you get a finite value, the system will be stable. So this is a simple check that once you are designing a system, add all the samples, the absolute value of all the samples in your impulse system. Remember, everything is around h of n. Saying add all the h of n, all the samples together. If you get something which is finite, you need not to worry about the stability issue. It will always give you a valid finite output. But if this h of k gives you infinite answer, it means that you are not sure whether what will you get. You may get valid values for some inputs, but there is no surety that for all inputs you get valid values. Okay? So you may get, you say, no, those people are saying the system is unstable, but I am getting, let's say you don't give any input, obviously you're not going to get any output. So you say I am getting valid values. So that is not valid. The validity is that for any input which is legal, you must get a legal output. Right? So it's, the condition says it's a simple proof, and the proof says that, okay, this is the convolution which will help you to compute an output sample. Okay, so let me say I take absolute of both sides, and I want this to be finite. If I want this to be finite, I can bring the absolute inside. If I bring the absolute inside, I will never get something which is greater than this, because here I am adding, I am multiplying and adding. Once I am multiplying and adding, I may be adding or subtracting depending upon the sign of this product. But if I bring the absolute inside, I always add, because whatever I get after multiplication, it is going to be positive. So this can be greater than this, but will never be less than this. So I am fine. If this gives me a valid answer, finite answer, means this will always give me a finite answer, because this can be greater than this but never less than this. So I say, okay, this is fine. If this is fine, then I say all my samples are the maximum permissible sample. Every sample, input sample, has the magnitude which is legal, which is L of x. So I replace all x of n minus k with L of x. Okay, so once this is L of x, it is a constant for this summation, I can bring it out. If I bring it out, then I have only this summation. This is finite, and if this summation gives me a finite value, multiply to finite number, you get a finite value. So it results that if somehow I can ensure that this is finite, okay, then all my y's will be finite for sure. So I need to worry about the summation. It's very difficult to check, obviously, that you usually your impulse response can be finite or infinite, right? So an impulse response can be finite or infinite. If it is finite, usually you need not to worry about, because if you are adding finite numbers together, you get finite answer. The problem is if you have an infinite impulse response, which we use a lot, then you need to about stability of a system, and stability says that all the samples, once you add them together, they give you a finite answer. Okay. This is stability. Let me not do this. ठीक है, next time. जी please. जी मैं बता देता हूँ. It's better अगर आपने if you took my digital design course, ठीक है, हमने इस चीज को यूज किया था h of k x of n minus k. ठीक है. If you write an equation out of this, only the equation will make more sense. ठीक है. इसलिए कि you say h of 0, x of n is the current sample. Let's say there are only 3 samples in the impulse response. ठीक है. h of 1 x of n minus 1 plus h of 2 x of n minus 2. It tells me that I need to use 3 samples to compute an output value. So in programming, if I'm programming this, I define an array which has 3 values. The first value I keep the current sample. Here I keep the previous sample. Here I keep the previous sample. So in another array I keep h0. These are constant values. h2. So I define 2 arrays. I initialize this array with h0, h1, h2, and I have this array which I always update. ठीक है. So I multiply this with this, this with this, this with this, add them, I get an output sample. Then I get a new input sample. What I do is I throw away this sample. ठीक है. I bring this one here, and fill the next here. Again I multiply, add, get an answer. ठीक है. फिर नया आ जाएगा. फिर I do this again and again and again. So this has a trivial realization, so to say. ठीक है. So it's just while you are implementing this in software, because signal processing means that you are going to implement it in software or hardware. So in next class will be a MATLAB, which Farhan will take. Will be a MATLAB workshop. We'll do a workshop, then you will get an assignment as well. So you get 2 assignments. One is a MATLAB assignment. The second one will be the theoretical. So you need to do the theory part, and then you need to go to the MATLAB and do the MATLAB part. So just to make sure that you are getting the correct answer.